Okie dokie. Going to now talk over some content for sections 8-4 and 8-5, which deal with testing and claim about a mean with both conditions when the population standard deviation is known or unknown. So essentially, we're applying hypothesis testing to means for these sections. Now, we'll focus mainly on section 8-5. So the two parts that these slides will cover. So part one is more section 8-5, which is the more realistic and commonly used case in which the population standard deviation is not known. And we'll address a little bit in for section 8-4 as if the population standard deviation was known, even though that is quite rare. So again, part one, we're going to start with when the population standard deviation is not known, and we're going to be using a t-test for any types of problems in a hypothesis test involving these ideas. So some notation just to kind of keep in mind still is n will still stand for our sample size, x bar will stand for our sample mean, and this mu sub x bar is what we'll use as the notation for our population mean. Notice this is the same notation for a sampling distribution mean, because essentially that's where population means are coming from most of the time. There's some requirements here for us to do these types of hypotheses tests is, again, this should be a recurring theme, is that we pretty much always want simple random samples. And now either or both of these conditions need to be satisfied. The population is normally distributed, or our sample size is bigger than 30. You notice either is an option this time. We don't have to have both of these satisfied. So we could just be working with normal distribution and a small sample size, or we could just have a big sample size that's bigger than 30. Now this time to find our test statistic, it'll still be similar to where we're taking our sample mean, subtracting off that population mean, or the claimed population mean, and dividing by our standard error, which will be made up of our sample standard deviation, and just divided by the square root of the sample size. Notice this time the square root's only going to the sample size. It's not going to that standard deviation as well. Now for running the test, we can use the p-value method, which using technology will be our best bet with the p-value method when we have to do the t-distribution. Because we can also use that t-table or table A-3 to find critical values if we're going to be using just the critical value method. And keep in mind, in either case, no matter what, our degrees of freedom is always just our sample size minus 1. And degrees of freedom really only comes into play with that t-distribution. And let's see, I just wanted to show this little visual of the t-distribution again, where there's a couple t-distributions here, and then the standard normal distribution, or z-distribution. So this orange one right here could be a t-distribution when the sample size would be 3. The red would be a t-distribution when the sample size is 12. Notice all of these still have that same bell shape. It's just as that sample size is increasing, that t-distribution is getting closer and closer to the standard normal distribution. Just re-emphasize some of those properties of the t-distribution. And is different for different sample sizes, like that picture just showed. And then the t-distribution has the same general bell shape again as that normal distribution. Now, its wider shape reflects the greater variability as expected when that sample standard deviation is used to estimate the population standard deviation. Something still similar, that t-distribution still has that mean of t equals 0, so like a t-score equaling to 0. And then the standard deviation of the student t-distribution varies when the sample size is greater than 1. And as the sample size gets larger, again, that t-distribution gets closer to the standard normal distribution, otherwise known as the z-distribution. Now, before we do an example, again, just a quick summary of the steps for a hypothesis test. Identify what claim you want to be testing, and then identify the alternative as if that original claim in R1 was false. In step 3, you're determining which of those two will be your null hypothesis and alternative hypothesis. Now, null hypothesis will still be typically the one that involves equality somewhere in the statement. and then the alternative will involve some form of not equals. And again, step 4, just need to choose your significance level. 0.05 is that most common one. Step 5, decide which distribution to use. For these test problems, we'll be using t-distribution typically. And find that test statistic and the p-value or critical value, or the confidence interval, depending on which method you're using. Step 7, after you run through the test, then either reject the null hypothesis or fail to reject the null hypothesis. And step 8, just restating your decision in context with non-technical terms. Alright, so we're going to start with this example where listed below are measures of radiation emissions in what I believe that is watts per kilogram, corresponding to a sample of cell phones. So we're going to use that 0.05 level of significance to test the claim that cell phones have a mean radiation level that is less than 1 watts per kilogram. Excuse me. Notice this is our claim that the mean level is less than 1 watts per kilogram. So this is a case where our claim does not have some form of equals in it. And so this is a sample of 11 radiation levels here, and we'd find that the summary statistics from those 11 are the mean is 0.938 watts per kilogram, and the standard deviation is 0.423 watts per kilogram. So just a quick requirement check, we can assume that this will come from a simple random sample, which will be the case for most of the examples that we deal with. And the sample size is 11, so it's not greater than 30. So then we'd want to check to see if it would be coming from a normal distribution or a relatively normal distribution, which we could check with a normal quantile plot. So don't need to worry too much about the normal quantile plots, but just a quick recap of how they work is we've got those actual data values along here on the x-axis, and expected z-scores essentially going along the y-axis, and then plotting the points according to that. And if the points follow roughly a straight line pattern, then we can say they came from a roughly normal distribution, which this will be close enough that we'll say they came from a normal distribution. And this is one way to check, but most time we'll be working with the problems that come from a normal distribution. Okay, so then to actually start with the hypothesis test. So step 1, we notice again that our claim is that cell phones have a mean radiation level less than that 1 watts per kilogram, is expressed in this form. Then step 2, just that alternative claim is just that essentially that mean radiation level will be greater than or equal to 1. Now, how we actually write that in the hypotheses is as follows, where the null hypothesis, we still keep it in an equals form when we actually write out the hypothesis notation. So that average is equal to the 1 watts per kilogram. And then that alternative hypothesis, where the average is less than 1 watts per kilogram. Now we're going to use, again, that stated level of significance of 0.05. And that's one of our more common alpha choices. Then step 5, because the claim is about a population mean, mu, the statistic most relevant to use is that sample mean, of course. And since our population standard deviation isn't known, we're going to use that t-distribution again. So first we got to calculate our test statistic, and we'll go from there to find the p-value or critical values that can give us our essential rejection regions. So we plug everything into that test statistic formula. So that sample mean of 0.938, that's our claimed mean of 1. And then that sample standard deviation of 0.423, our sample size of 11. Once we would evaluate all of that, we should be getting a test statistic of about negative 0.486. And this is what we'll use to either find a p-value or compare to critical values. Because again, this is a t-score, is essentially what we just found here. Now, the way our t-table and everything is set up for this class, the critical value method actually works pretty well for these types of problems. So because the test statistic of negative 0.486 does not fall in the critical region, bounded by the critical value of t equals negative 1.82, we'd fail to reject the null hypothesis. Okay, now how we find that negative 1.812 is we'd be using the t-table, and just keep in mind our alternative hypothesis was saying that the mean was less than 1. So that's why this one is a left tail test here. And now how I find that negative 1.812, I come to the t-table, and I want to look for where I've got the area in one tail, and this area is corresponding to that significance level, or alpha of 0.05. So I'm going to look in this column here, and my degrees of freedom still just that sample size minus 1, so my degrees of freedom would be 10 in this case. So I just see where those meet, and I see that my critical value is that 1.812 right there. But since this was a left tail test, I just go ahead and make that 1.812 negative. And then that's how I got that critical value of negative 1.812. Now, since my test statistic was negative 0.486, essentially what that shows me is that this is not as extreme as these values that would be rejected, because that red region is still the rejection region, or essentially the more extreme region. Now, you can also find a p-value with forms of technology for this method of hypothesis test. If you have a TI 83 or 84 calculator, you can use that to get that p-value. If not, and there's also a way to find the p-value on Statsmetic. I'm going to show how to get to that using Statsmetic. Just going through same navigation here to get to our Statsmetic applets, and I'll show you which applet to use here. Once it loads up. Okay, so this time I want to come all the way down to the bottom, and I want to do a one sample t-test for a mean. Scroll to the top, and let's see, the variable name this time is essentially cell phone radiation is what we're testing in this example. And the input, I want to be inputting the mean and the standard deviation. The mean from this sample was that 0.938. That standard deviation was that 0.423. That sample size was 11. I click begin analysis, and essentially it'll just take me to where it'll allow me to do the test I want for the p-value. Now notice it's just a one sample t-test, keep it that way. The alternative hypothesis, I change it to this less than, since that's what my alternative hypothesis was. And that hypothesized mean, or the claimed mean, is, I'm going to put 1. And then just perform my inference from there. Notice it gives me a t-value, or a t-score, critical value of negative 0.486, which once we do some rounding, it is about the same as this t-value here of that negative 0.48485, so on. And it gives me a p-value of 0.319, which is also pretty close to this p-value of about 0.319. Now that p-value is much larger than our significance level of 0.05, so in either case we would fail to reject the null hypothesis, because that's a probability that's not as extreme as that 0.05 essentially, or not more extreme than the 0.05. So we turn all of that into context with non-technical terms. So because we fail to reject the null hypothesis, we conclude that there is not sufficient evidence to support the claim that cell phones have a mean radiation level that is less than 1 watts per kilogram. All right, and I'm going to stop there to finish up in the next part.